So, hello, we started talking about the peculiar behaviors of sequences, simple behavior of sequences. And the first is probably the most well known, namely convergent sequences. So, what does it mean, convergent sequence? Let us start by an example, and the example can be taken as the following. an, our sequence, is minus 1 to the nth power divided by n, with n belonging to the set of naturals with the exclusion of the zero. Okay, so let us give a look to the behavior of the sequence. And so we have a0 is not there because n is different from 0, and then a1 is minus 1 here. Then a2 is plus 1/2. a3 is minus 1/3. Then a4 is 1/4, and so on. Here there is 0. And we see that the behavior of the sequence is to fall near 0, never approaching 0, and trying, in some sense, to shrink around 0 from both sides. Okay, this is the qualitative behavior. And so, what is the meaning of this behavior? How can we describe this behavior? There can be many descriptions, but the description that at the end turned out to be the most useful in terms of the theory is the following. If you consider what is called a neighborhood of 0, so something that lies here, then sooner or later the sequence is trapped there. The sequence enters here and never get out. And the strength of this definition is the following, is that we are not talking about one specific neighborhood of 0, but for every neighborhood of 0. So we can focus our attention to neighborhoods that are smaller and smaller, and sooner or later the sequence will go there and will never get out of the neighborhood. Okay? This is what we choose in order to describe this behavior. And so let us try to write it in mathematical terms. The idea is the following. Choose an interval, however small, centered at 0, and then what you see is that the sequence will lie eventually means from some index n on. The sequence will lie eventually inside such interval. So let us try to understand what is the meaning of that. Here you have 0, here you have an interval around 0, and let me call this interval again epsilon minus epsilon epsilon. Okay? I'm stating that for every value of this epsilon, however epsilon is small, sooner or later the sequence will fall here. So for every epsilon larger than 0, which means for every interval centered at 0, the sequence will lie eventually. Eventually means that there exists an index n bar natural index n bar, such that whenever n is larger than n bar, so after n bar, the sequence will fall here, which means that minus epsilon less than an less than epsilon. Okay? This is the definition, and so let us explain. For every epsilon larger than 0, this translates for every interval centered at 0. There exists n bar in n such that for every natural n larger than n bar, this means eventually. Okay? After some specific value of n bar, such that an is trapped there. Okay? The sequence lies eventually there. This expression is sometimes given as absolute value of an less than epsilon. So, okay, now one can introduce another word that will be defined immediately after. So, in this case, 0 is called the limit of the sequence an. And one says that the sequence an converges to 0. But of course, one can think of sequences converging but not at 0. So, here we have a more general definition of convergent sequence. So, I give you the definition and we will discuss. What we have to generalize, we have to start to consider a generic an, but in particular the fact that the limit is not 0. So, we say that if an is a real sequence it is said to converge to the limit L in R if. Now we have to generalize what we wrote here. But instead of 0, we have some number L. Again, we want to say that however close we fix a distance to L, eventually the sequence will fall inside this distance, inside the interval centered at L, whose size is exactly the distance we fixed. So the distance is epsilon. For every epsilon larger than 0, then the idea of eventually, from a certain point on, from a certain label n bar on. So there exists n bar in n, such that whenever n is larger than n bar, then we have that the distance between an and L, so the distance here can be written like that, is less than epsilon. I want to stress this fact. Absolute value of an minus L is to be interpreted as the distance measured on the line between the 2 points, or the numbers an and L. You can easily understand why is it so, because here you have, if this is the situation, the distance here, so the length of the segment of this interval is L minus an, which is exactly equal to the modulus of L minus an, since L is larger than an. Vice versa in the other situation. So this is also the modulus of an minus L. The other situation is the following. Here you have L, here you have an, and again you have an minus L, and this is again the modulus of an minus L. And so, in this case, one writes, so that the limit of an is equal to L. Or sometimes lim for n going to plus infinity of an is equal to L. But this writing is somewhat pedantic. It's somewhat pedantic because here we deal with limits of sequences, and it is clear that this and it is clear that the limit here, when you are talking about sequences, can only be the limit for n going to plus infinity. Okay? So let me explain again this definition. I want to insist a lot on this definition because it is really important. Okay, today many important notions, and the notion of soup, and now the notion of limit. It is the first time you see the notion of limit, and so let me explain it a bit. You have in the first representation here you have L, and so here you have L plus epsilon, L minus epsilon, and however epsilon is small, it does not matter. Sooner or later the sequence will fall here inside after some n bar. Of course, another important idea is that the smaller you take epsilon, the larger will be n bar. So here L plus, let me call it epsilon prime, L minus epsilon prime. Okay, in general, the smaller epsilon, the larger m bar. So another important message is that n bar depends on epsilon. In particular, I ask you to meditate, to think of what happens if we change the definition of limit simply by exchanging the first parts, namely, if we say there exists n bar in n such that for every epsilon larger than 0, whenever n is larger than n bar, we have an minus L less than epsilon. So is this definition equivalent to the first one? This is the question, and if not, why? Think of it, we can discuss tomorrow. I want you to understand very well this definition. Okay? So, another representation that can we have, is the representation, concerns the representation of sequences as graphs of functions. So as things like this, you have a limit L here, here you fix epsilon, and you have here L minus epsilon, L plus epsilon. And so what you construct here is a stripe of width 2 epsilon. Okay? So what you are saying is that sooner or later, so the sequence can enter into the stripe and then go out, but sooner or later the sequence will enter the stripe and never get out. Okay? And of course you can choose a thinner stripe, for instance this one, so a new epsilon which is smaller than the previous one, and again you have that sooner or later the sequence enters the stripe and never get out. Of course, since epsilon, the new epsilon of the blue stripe, is smaller than the previous epsilon of the red stripe, the n bar will be smaller. So if this is, will be larger. This is L plus epsilon prime, this is L minus epsilon prime. And for instance, in our picture, this is the n bar related to epsilon, in the sense that after this point the sequence always falls inside the red stripe, but in order to fall inside the blue stripe you have to wait a bit more. So this is n bar of epsilon prime. So now let us test this definition with a strange exercise. This is not the exercise of a computation of a limit. I know you are very strong in computing limit, but I want you to reverse the point of view and just use the definition of limit not in order to compute a limit, but in order to prove that a given limit is true. So this is an exercise that helps you to understand what is the limit. Okay, it is not a sort of performance exercise on showing how are you strong and so on. So this is the spirit of this exercise is much simpler. You want to show, to prove a limit, not to compute a limit. So the text of the exercise is prove that limit of n squared plus 4 divided by n squared plus 1 is equal to 1. So another notation that I will use extensively because it is very fast and simpler and more intuitive is the following: n squared plus 4, n squared plus 1 tends to 1 with a sort of long arrow. Okay? So let us denote, for simplicity, an is equal to n squared plus 4 divided by n squared plus 1. And what is the philosophy of the exercise? We just apply the definition so we must choose, first choose an arbitrary positive epsilon. Second, find n bar such that for every n larger than n bar, we have that the distance between the sequence an and the candidate limit 1 is less than epsilon. We have to fulfill these two steps. Okay? So, following, it is not completely trivial, even though it is just the application of a definition. The first time you see it, it is not trivial at all. So, first, we say just let epsilon larger than 0 arbitrarily chosen. Okay? We aim, our aim, at knowing for which values of n one has the inequality an minus 1 less than epsilon. Okay, so it is just an inequation in which the unknown is n. Okay, this n is the unknown. Of course, let us write it in an explicit way in order to understand what we are talking about. We are talking about an, which is n squared plus 4 divided by n squared plus 1 minus 1. We want it to be less than epsilon. The unknown is n, I repeat. So this is just to say n squared plus 4 minus n squared minus 1 divided by n squared plus 1 less than epsilon. So the two n squared cancel, so we end up with 3. Divided by n squared plus 1 less than epsilon. So this is 3 less than epsilon n squared plus epsilon. So again, n squared must be larger than 3 minus epsilon divided by epsilon. Okay? So here intuitively, the exercise is solved. Intuitively, one could say, okay, it is sufficient to take a natural number n which is larger than the square root of this quantity. But here, we want to do mathematics with a certain rigor. So when we think of the square root of this guy here, we have to consider the possibility that this number is negative. So you cannot compute its square root. So how can we do? The first thing is to be sure that this number is not negative. So first, we say if epsilon is larger than 3, because I just said epsilon larger than 0. I did not say epsilon small or things like that. So if epsilon is larger than 3, then this quantity 3 minus epsilon divided by epsilon is negative. So this means without computing square roots, this means that 1 is always satisfied. Is satisfied for every natural n. Why? Because here you have a square. The square is always non-negative. Here you have a negative number. So this is always satisfied. And then we have to determine n bar, and we just say that choosing whatever n bar, for instance n bar equal to 0, we conclude that for every n larger than n bar, we have that an minus 1 is less than epsilon. Because here we simply go backwards from here, here, and here, and we end up here. But this is the trivial case, if you want, where epsilon is large. Let us go to the second case, which is epsilon less or equal than 3. Of course, epsilon must always be positive. So what we have here is that 1 is this inequation here. 1 is satisfied for every n larger than square root of 3 minus epsilon divided by epsilon. And of course there is such n, because the set of natural is unbounded. But again, this is correct, but we want to isolate an n bar, so in order to define n bar, we must introduce rigorously the integer part of x. I already did it in the lecture of in the question time of last Tuesday, but I want to do it again. So here we have a definition, integer part. That says the following: consider any real number, then you define x, which is the integer part of x. This is the maximum of z. of an integer z such that z is less or equal x. I recall you the picture I already showed you at the blackboard in that question time. And so here we have this guy here. For instance, if this is x, the integer part of x is the largest integer not larger than x. So this is the integer part of x. Okay? And I recall you the example we did. Namely, the integer part of 3 and of every integer is the integer itself. The integer part of pi is 3. Remember that the integer part of minus pi is minus 4. Follow the definition if you don't agree with that. An important remark on the integer part is the following. You see it from the definition here and also from the picture here. The integer part cannot exceed x. The integer part of x cannot exceed x, and x is always smaller than the integer part plus 1. So this is the double inequality, integer part of x less than or equal to x, which is strictly less than integer part of x plus 1. So be careful, because this is strictly less than. Okay? And now let us go to our previous exercise. So we consider n bar. We must feed n bar with an integer number. This is why I do all this messy thing, the integer part. But it is very simple conceptually. I repeat, the idea is that this may be not an integer number, so it cannot be n bar. But its integer part is integer, so I say that n bar is equal to the square root of 3 minus epsilon divided epsilon integer bar. Now, we have that n bar plus 1 is larger than 3 minus epsilon divided epsilon under square root. So by applying the second inequality, in 2. Okay. Then, for every n larger than n bar, we have that n is larger than the square root of 3 minus epsilon divided epsilon, and then we have that an minus 1 is less than epsilon. This conclusion can be recovered running backwards through all passages. Okay? So I ask you to think a lot of this exercise, because the purposes of this exercise are twofold. First, understand the notion of limit. Second, understand this use of the integer part. So, and then I stop here and I go for the last part of today's lesson.